as you know, you have data, you project it down to some four-dimensional space, this linear space here, and you do it in a way such that the distances of these projections are as small as possible. Okay, so the sum of the squares of these distances is small. So this, as you know, is an extremely useful technique, and it corresponds to the reality actually that often data does not lie uniformly distributed in a high-dimensional space. You know, if it did, then, for example, if you think about digits and handwritten digits, then they would not look like digits, right? If things which are uniform, just like a random, white noise. In other words, there's a lot of structure to real-world data, and this linear structure is one of the simplest we can try to extract. And it's indeed the case that data often lies close to a linear manifold. So I don't know how much you've gone through the mathematics of PCA before. Did you do? Who's gone through the derivation of PCA? You did this?
We did it in
You derived the whole thing?
Yeah, I think it's like the limit of the PPCA, isn't it?
The limit of
the probabilistic principal components.
We didn't derive the simple one.
Okay, it is. It is the limit of that. So
we assumed no now.
So what we'll do is, I'll do it anyway. So, okay. So what we're going to say is that each data point xn is approximately then given by, this is going to be a point on the plane, okay, the hyper plane. This space, rather, actually, subspace. Okay, so each point in the subspace can be described by, say, some constant vector, say c, plus some amount in this direction, plus some amount in that direction. Okay, and that will give us a point lying on this space. So the coordinates are going to be, these y's are going to be the new sort of coordinates. In this case, example, there, x is a three-dimensional vector. There will be two y's. How much you go along one direction, b1, and the other one, how much you go along the direction, b2. And that puts you somewhere in this three-dimensional space. And we'll call that, that point on the plane, the subspace we'll call x and tilde. Okay, so if you like, we can call these BJs, basis vectors. It's maybe a bit of a bad term, but so we could stack them together. We'd have, say, m d-dimensional basis vectors. And these new y's are the coordinates. So we want to find two things. We want to find these b's, what is the best description of the subspace, and what are then the corresponding best coordinates of these y's. In a way that will minimize the squared reconstruction error. So we want to take x, the original x, look at its reconstruction, and then have the squared, minimal square error over sum over all the dimensions and then all the data points. Okay, so if you do this, you'll rapidly find that the optimal C is basically just given by the middle of the data. This is an easy thing to figure out just by differentiating. So what we'll do is that just for simplicity, and I'll just assume that the data has got zero mean. So we do this centering operation that we talked about last time. So in other words, you just subtract the mean from the data and find the new data points. But I'll also call them x. Okay. So this objective function, the squared error, is given by this. This is now, there's no c anymore, so this is the reconstruction. So I'm using various different upper and lower indices just for fun. And we can write this in another way using sort of matrix algebra. We can write this as this trace of this corresponding matrices on the right, where this matrix X now is the sort of the data matrix, the stack of the data matrices. B is what we saw before, and Y is also now the stack of the corresponding Y vectors. Okay, so you can see that this looks like the ith element of X minus some matrix multiplication here, by, and we're squaring it. And if you work this out, you find that this is actually the algebraic representation. Okay, so what I'm going to try to say now is that, well, essentially it doesn't really matter too much, but you can place inside here, you can place, let's say, some orthogonal or orthonormal matrix, say, whatever I call it, Q or Q tilde Q, I think. So if I were to place within here, Q times by Q transposed, Q transpose is the identity. So that means I can, rotate B, I have BQ, and I have Q transpose Y here. So that means that I can, I can perform some arbitrary rotations on either B or Y, and I'll still get the same objective function. So that means there's a kind of scale invariance here. I mean, a simple way to think about it is if I multiply this by a factor of 10 and that by a factor of 1 over 10, I'll get the same answer. And more generally, I can multiply it by an orthonormal matrix, and that will also give me the same answer. So there's a little thing here which says that, a little argument which says essentially, with lots of generality, you can assume actually that this matrix B has got this orthonormal constraint, and you will not lose anything. It's equivalent in some sense to say setting kind of the length scale of B, essentially, but you can make this restriction, and you don't lose anything at all. So in the interest of time, I will let you read that argument on your own. Okay, so that's good. Then we just go back. That argument is just to say that we've got this. We can say B effectively equal, so this is orthonormal, and then we can differentiate the objective function, say with respect to Y. We're going back to this one here, and when we solve this to set it to 0, we find that the optimal Y's are given by this. In other words, the optimal Y's are given by B transpose X. So that's an easy one to do. So now what we can do is we can plug this solution for Y's into the objective function, just to get now a function only of B alone. Okay, so the objective function was given by this. Using the fact that Y is equal to B transpose X, that means we can write now this objective function just as the trace of this matrix here. Okay, you can see that, right? So B transpose Y, I take a factor of X here on the left, X transpose, take a factor of X on the right, I get I minus B squared basically in the middle. So I minus B transpose, this is idempotent, as they say. So in other words, if you multiply this now, you get I squared, so it's I minus B transposed. So minus 2B B transposed, then plus B transposed times by B transpose. But B transpose B is equal to the identity, so you get I minus 2 B transpose plus B transpose. So it's I minus B transposed. Okay, because of this orthonormality constraint. So that's nice. So the whole objective function simplifies to this. I can use this circular sort of thing. So I can basically the trace of AB is the same as the trace of BA. So I can take this to this side here. I'm left with this. Okay. So that's good. Now I just need to maximize this. So minimize this with respect to B, subject to B being an orthonormal matrix, and then I'm done. Okay, so just out of interest to, what is this matrix X transposed? Well, because we have zero mean data, actually this is just a covariance matrix. Just rescale by a factor of n or whatever n. It's up to you how you define it. For some reason that I don't remember, I decided to write 1 over n for the sample covariance matrix, but it doesn't really matter. If you put n or n minus 1, it's irrelevant. Okay, so that means that we can write the objective function. So we have this I minus X transpose, so that means we've got this, so S minus, trace of S BB transpose here. Scale by 1 over n. Okay, so that's that. So then the general case, if it hadn't, you would find that if we had not actually zeroed in this data, the whole thing would go through, except that we just got to compute the sample covariance matrix by taking off the mean. Okay, so what we want to do then is to maximize, to minimize this expression here, okay, with respect to b. Well, obviously the first term doesn't depend upon b, so we can forget about that. So it's equivalent to maximizing this trace term subject to the orthonormality constraint, or to minimizing this term here. Okay, and this orthonormality constraint is that the B transpose B is equal to the density matrix. Okay, so that means that you basically want every element of that to be to be equal, basically. So that just means you've got a Lagrange multiplier, let's call it L, per element of this matrix. Okay, so we can write that in this sort of more compact way, instead of summing over the Lagrange multipliers. So explicitly, we can just write it as a trace operation like this. It's the same thing, basically. So L is the matrix of Lagrange multipliers, and it's symmetric because B is symmetric. This B transposed is symmetric. So that's, you only need to say constrain, 1/2 of this thing. Okay, so if you now take this as your Lagrangian, and you differentiate this with respect to B, you are free to do that and test your linear algebra skills. You know how to differentiate. I mean, you just, the worst case, you just go back to component notation, differentiate with respect to B, ij, and equate to 0, and then rewrite that as a matrix in matrix form. And you get that SB is equal to BL. That's the solution, okay, to this thing. So so S is known. You don't know B, and you don't know L, okay, except that it's supposed to be a symmetric matrix L. And B is supposed to be an orthonormal matrix as well. So this though looks then like an eigen thing. You recognize that an eigenvalue, if B were the eigenvalues of S, so the eigenvector matrix of S, and L was the corresponding diagonal matrix of eigenvalues, then that would satisfy that actually, because then S is symmetric, so that means that the eigenvectors are orthonormal, and you can then have this as a symmetric matrix because that's diagonal. So this means that the eigen system would be a solution of this equation, or at least one solution. Okay, so that's how you get that, and you're automatically then satisfied this orthonormality of B because the eigenvectors are orthonormal. Okay, so if you want, then you can just plug that solution in. So in that case, this term SBB transpose is just a trace of the eigenvalues. So the whole objective function then becomes minus the trace of the eigenvalues, the sum of the eigenvalues, plus trace of S, where the S is a constant, so that's not a problem. So basically that means that we've got this is the negative sum of the eigenvalues. We want to minimize this. That means that we want to take these lambdas which are maximal, basically. So the way to minimize E says that you want to get the biggest n eigenvalues out of this decomposition. And similarly then the residual error, once you've done that, is equal to the sum of the eigenvalues that you didn't include. So you've got d-dimensional vectors x, and so this is, you take the first say 10 eigenvalues, and then the remaining ones for the actual decomposition, and then the remaining error is given by the other eigenvalues you did not include. Right, not the first 10, the highest values. Okay, so that's a solution to this least squares problem. Just to, unless in case this was not emphasized previously for you, just bear in mind that this solution is not unique at all, right? So all we're trying to do is to define this subspace. That's it in this case for the linear reconstruction. So you can define this in principle any way you want. You could say here, I define this this plane by say 2 orthogonal vectors and some C, but I could define the plane in any way I want. I mean, I could define them, any point, and sort of two vectors here. They don't even have to be orthonormal. Just have to lie in this plane. So that means there's a whole space, of solutions for this least squares problem. PCA provides one of them, but there's no unique solution to this problem. It's from the least squares perspective. Okay. So then an interesting question is, well, PCA, when you do the eigendecomposition, that is unique. There's only one eigendecomposition. So if, on the other hand, actually the real, there's a whole space of equivalent solutions here, what does the eigendecomposition actually correspond to geometrically? So it seems to do something else as an additional thing that it's doing. So you can also think about this in terms of maximum variance. So what you could do is you could say, well, let's look at, say, a data point xn, and we project it down, say, to one dimension in this case. So let's say we project that to a scalar y, okay, yn, through some matrix. In this case, it's a vector b. Okay, we want to make this projection such that the projected data points have got maximal variance. So let's look at the, each yn squared. So because if x has got 0 mean, then y will also have 0 mean. So let's compute the variance of these scalars, okay, projected down. So that's given by, this is b transpose xn. So that's given by the sum of the squares of y squared, which is this. So we can just rewrite that as b transpose xn, xn transpose b, pull out that, put the summation inside, we've got this. Okay, so this is again the covariance matrix appearing here, scaled, and so we've got b transpose sb, some scale. Okay, so if you want to find now that b, so unit length b, which say maximizes this expression here, that corresponds to b being aligned with the the principal eigenvector of S. Right? Because if you think about, going back to our first week, S, the decomposition, its eigendecomposition is the sum of the outer products of lambda I times by ei transposed. Right? So if I were to set b to be equal to the first eigenvector, that means that it will be orthogonal to all the other ones, and this term here will simply be equal to the largest eigenvector, eigenvalue. That will be the maximal value that this could ever take. All right. So what that's telling you in this case is that if you were to project, so that's the same solution as the PCA that gave us. Right? And if you then, you can say, well, if I were to now, say, project down to a second dimension, and I want that second dimension is orthogonal, another b, to my first dimension, okay, so I'll get say a y2, and I want that dimension to be, that b projection for that to be orthogonal to my first b, this one here. Then you'll find that actually that corresponds to the second largest eigenvalue, etc. And you can build this up then. So what that means is that the total PCA, the PCA solution corresponds to this maximum variance, so that you are essentially projecting along, you find a direction such that the projected data along those directions has maximal variance. So if I don't know if I can show the picture very well, but so it's a little bit kind of spread out, but I'm hoping I have a picture of this. Yeah, here we are. Right. Okay, so that means here's two-dimensional data. We're going to project down to one dimension. So another way to think about this is that this dimension here is the one which, when the variance of these black points, okay, is large. And there is no other projection which has a larger variance of black dots. So in the one-dimensional case, for the unit length of the projection is kind of unique, but so it's a bit trivial. But yeah, in general, it's that's what's going on. So the invariance of the least squared reconstruction error is broken by PCA, and it corresponds to these maximal directions of maximal variance projections. Okay. So here's some examples. Here's some digits, handwritten digits on the top. These are the corresponding reconstructions of them using 5 eigenvectors, 30 and 100. So you see as you go increasing the number of eigenvectors, so that the space in which you're projecting the data down, that the quality of the reconstruction is improving. And these data points are living in, I don't know, something like 400 dimensional space, something like that. So you get quite a reasonable reconstruction using, say, 30 dimensions rather than the 400 or whatever it would be data dimensions. Yeah.
Where do the 400 dimensions come from?
They come from the size of this digit. So it's like, say, 20 by 20. So each digit then corresponds to a 400 dimensional vector. And then I'm just plotting it in this vector in this way. So what you should see is as you go down in the number of eigenvectors, that these reconstructions will start to look more like the mean of the data, actually. Okay, so you'll see less distinction between these projected data points than you would as you go to increasing the number of dimensions. Okay, so the one thing to say though is that what you don't want to do in practice is when you've got, say, images like 1,000 or million dimensional images, quite okay, 1,000 by 1,000 pixels is not so big. Then how big would the covariance matrix be? Well, it would be 1,000,000 by 1,000,000, right? You don't want to be computing you don't want to try to put into MATLAB, please get me the eigen decomposition of this 1,000,000 by 1,000,000 matrix. It will fall over. Even big computers will not be able to do that. Really, really big computers. Okay, so you need to do something else. And there are a couple of things you can do. I'll tell you maybe the more modern thing to do, but you may also hear this thing, Cahunan-Lerve transformation. But this is another way to do it. So this is through SVD. So and the point about this is we don't want to at any point explicitly construct the covariance matrix, because we'll be dead. Even storing a 1,000,000 by 1,000,000 matrix is already a pain to do, right? So what we'll do is we'll consider the SVD of X. Okay, so let's say U, D, V transpose, where U and V are corresponding orthogonal matrices or orthogonal matrices. Then remember that the covariance matrix, I'm assuming the data is zero mean, is given by X transpose, right? So what is that? So given this SVD, it's given by this expression here. But V is an orthogonal matrix, so that's the identity. So D is diagonal, so we're left with UD squared U transpose. And this is good because remember that U is orthogonal, so this actually is an eigen decomposition now of X transposed. Because this is an orthogonal matrix, this is a diagonal matrix, and this is an orthogonal matrix. So this is the form U is if U can be taken as the eigenvectors, D squared is the corresponding matrix of eigenvalues. That's equivalent to an eigen decomposition. Okay, so in other words, you can get the eigen decomposition by forming the SVD of X directly, and then U's are, for throwaway V, you don't need it. U are your eigenvectors, and your eigenvalues are given by the square of D. Yeah, so D. Okay, and you just take the you want to take the you want to take, well, you have to cause whatever package will, you want to, obviously this is a full decomposition, so what you want to do is you want to take the matrices which correspond to the largest elements of D. So it depends what your package does for you. Sometimes they come back sorted, sometimes they don't. Sometimes you have to figure out which are the largest elements of this D. So I don't know, I don't remember what MATLAB does, but and there are other packages which recursively try to spit out the singular value decomposition, largest one first, and then you just stop after you've got however many you want, basically. Okay, so this is much better to do. So this way, the computational complexity is assuming that n is bigger than d, is equal to n times by d squared. Okay, that's the computational complexity. With no, not a d squared storage cost. These are some lovely people from Olivetti. We take a bunch of them, 120 training images. Each pixel is okay. So it's they're quite big actually. It's 92 by 112 pixels. So 10,000 dimensional vectors, and we're going to try to represent these. There are not many images actually, but we'll try to use PCA or SVD images. So these on the right are the singular values, sorry, the PCA reconstructions. These are the, okay, so on the left are the reconstructions using 49 eigenimages. Okay, eigenvalues, basically, eigenvectors. And these are the 49 eigenvectors. So for some reason, the psychologists, they love these pictures, and people think there's something really remarkable about these eigenfaces. For me, it doesn't do much for me. So what I wanted to show you, and unfortunately we won't have time, is I just do the wait for next week's wonderful Flash Gordon kind of thing, but we will talk about something else like this. Will be the thing to think about next week. This is also a reconstruction of these images using something which I think is a little bit more interesting. This is kind of a non-negative matrix factorization style technique, but done in a probabilistic way, and you'll possibly find it useful. Okay, so that's it.